So in this unit, we're going to start to represent these tiny, tiny particles, atoms, and molecules with symbols so that we can keep track of them on paper. First, I'm going to show you the chemical formula for vinegar. This is called a molecular formula. Because it lists how many atoms of each type. The molecular formula for vinegar is C2H4O2. Well, actually, that's the formula of the solute in vinegar. There's also water in vinegar as well. But the solute in vinegar, C2H4O2, that's its molecular formula. That means that each molecule has 2 carbons, 4 hydrogens, and 2 oxygens. Now, I can represent that more clearly as what's called a structural formula. And when in that, I see the detail of which atom is connected to which atom in the skeleton. This is a skill we'll develop towards the end of this course. For now, this is authoritative knowledge. I can draw a structural formula on paper, or I will also like to show you models with plastic spheres, like Dalton's indivisible spheres, to represent that. And in my model kit, the black balls usually represent carbon, white is hydrogen, and red is oxygen. More examples of that later. So that's the difference between a molecular formula that lists the number of atoms and the structural formula that shows actually what's connected to what. We're going to want to write the formulae for a lot of compounds, and I know you have some experience with that from high school. And I want to stay absolutely clear with you on what I think you already know and what I don't think you already know. So let's look at the elements that exist as molecules. And I don't want any surprises. I'm going to define my terms. Molecules are groups of atoms held together by covalent bonds. More on covalent bonds later. But the short version is covalent bonds are shared pairs of electrons. Some elements aren't happy in existing as a monatomic element, a single atom of each type. I see on this picture what looks like the number 7. And I think you have experience that those elements exist as diatomics, 2 atoms stuck together to make a stable molecule. In other words, the way we find nitrogen in the air is as N2. The way we find oxygen in the air is as O2. So those elements on that corner of the periodic table that form the shape of the number 7 are diatomics. The other one that's diatomic is on the other side of the periodic table, shown here also in light blue. Hydrogen's standard state is H2. A hydrogen atom by itself wouldn't be stable. H2 is. I think you know that. I think you bring that with you from high school, and if you don't, you're going to learn it right away. Just for interest, I'll show you how some other elements exist. I don't think that you necessarily know that. So the way that phosphorus exists is as P4, and there is a structural formula written here beside the molecular formula. Again, the structural formula shows how those atoms are attached to each other. I have a molecular model of a phosphorus molecule right here. I do not expect that you're going to remember that phosphorus forms P4. We're not into trivia here. I like the general pattern of the diatomics. I show you that phosphorus just for fun, and I'd remind you whenever you needed it. Again, just for interest, sulfur forms a cluster or a molecule involving 8 sulfur atoms. There's the molecular structure, S8. And here are different forms of the structural formula of S8. I've got my molecular model here. Sulfur forms what those whimsical chemists call a crown structure, where it goes up, down, with 8 atoms around the ring. Just for fun, again, those of you who've been to Stanley Park and looked over to what is it? I'm not from Vancouver. West Vancouver, North Vancouver. There's piles of yellow on the waterfront over there. Those are piles of elemental sulfur, S8. Carbon, just for fun, has a couple different forms it can form, and you might know the name of what we call these different forms of an element. These are called allotropes. Same element, but the atoms are packed together in different ways. The first version of carbon, elemental carbon, is a diamond in which the carbon atoms are arranged in a network. And in this picture, you can see that each carbon is attached to 4 other carbons in the network. I have a model here that's not really a diamond, but it's the same shape. In diamond, all of these would be the same gray atoms, the same black atoms for carbon. But here you can see in this model that every atom is attached to 4 other atoms in a network. This is held together by covalent bonds. It's really strong. And that's why diamonds are so hard, because it's held together by covalent bonds. Really hard to break. Another allotrope of carbon is graphite, and you find that in various places. In a pencil, the pencil lead is made of graphite. Graphite is also used as a lubricant for ball bearings. And the reason is that in graphite, the carbon makes sheets in which the carbon atoms are bonded to other carbon atoms in 6-membered rings. There's covalent bonds all through the sheet, so each sheet is very strong. But between the layers, where's my pen gone here? Whoops, over here. In between the sheets, there are no bonds at all. So those sheets can slide very easily past each other, and that's why you can rub graphite off onto your paper when you're using a pencil, or that's why it's a very good lubricant. Now, some people might think chemistry is stoichiometry calculations and that stuff. I think what chemistry is relating structure to behavior. This is the first real chemistry I've told you about. There's one more allotrope of carbon, and we will talk about it very soon as an example. It's called a buckyball, or Buckminsterfullerene. And in buckyballs, 60 carbon atoms are stuck together in the shape of a soccer ball with pentagons and hexagons on the surface. That has different properties again. That behaves like smaller molecules do. So again, that's just for fun. I don't expect you to know what the allotropes of carbon are. I expect you know which elements are diatomic. As we're talking about formulas here, I want to distinguish between molecular formulas and empirical formulas. We've already defined molecular formulas. We've shown that the molecular formula shows all of the atoms that are in the compound. So for water, the molecular formula is, H2O. To make a structural formula for that molecular formula, you would see an oxygen bonded to 2 hydrogens. There's another compound that has both hydrogen and oxygen in it, hydrogen and oxygen. And I don't need you to know this, but if you want to show off and tell me what that's called. That's hydrogen peroxide. And it's got 2 oxygen atoms and 2 hydrogen atoms in it. With these 2 compounds, I can illustrate the difference between a molecular formula, which shows the actual number of atoms in the molecule, and the empirical formula. An empirical formula has that ratio of atoms in lowest terms. So for hydrogen peroxide, H2O2, there's a common factor of 2 there. The lowest ratio of atoms is just HO. So the empirical formula is the lowest ratio of atoms. The fact that the empirical formula for hydrogen peroxide is HO does not change what the molecule looks like. The real molecule is H2O2, but the formula is HO. That word empirical is defined in this context as the lowest ratio of atoms, but as we'll see in later work, what empirical really means is determined from experimental evidence. We will look at the experiment that leads to the empirical formula, and you will see that the best we can do from that work is to find the simplest ratio of atoms. For hydrogen peroxide, the molecular formula and empirical formula are different, but for water, the empirical formula is the same as the molecular formula. That ratio, 2:1, was already in lowest terms. My final example on this one is that is C6H6, which just for fun is the formula for benzene. And it turns out that in benzene, the 6 carbons are arranged in a ring, some single bonds, some double bonds, and each carbon has a hydrogen. Benzene is a component of petroleum. When you distill crude petroleum, this is one of the fractions that comes off. That's the molecular formula, but you can anticipate me and write the empirical formula. CH. All right. Now that we know about formulas, we're ready to go on and write some more formulas with more compounds.